Hello everyone, my name is Ka Ho Tam. I'll be talking about an experiment on a proposed method to improve measurements in histopathology by utilizing uncertainty information obtained from Bayesian neural networks. A core aim of computational histopathology is to assist pathologists to predict the clinical outcome of an organ based on the limited tissue from a biopsy. However, since typical histology datasets contain no more than the order of 1,000 samples, direct prediction of the clinical outcome using an end-to-end neural networks is very difficult. Instead, we often resort to use neural networks to obtain clinical measurements of features inspired by domain knowledge. Evaluation of many of these features hinges on the accurate segmentation of individual tissues. Artifacts in the test datasets, for example, as below, can lead to significant errors in the counting of instances as well as the derived measurements. Because many of these measurements are handcrafted based on instances, it can be difficult to find a generalized method of propagating segmentation errors to the downstream statistics. Luckily, in histopathology, we're usually just interested in obtaining the distribution of measurements in a given slide. So the question is, can we bypass the complexity and ambiguity of instance counting? Given the established methods of extracting classification uncertainties in neural networks, can we use them to improve the estimation of histology-based measurements? There are already a good number of publications on how to evaluate segmentation uncertainties using Bayesian neural networks. The majority of these focuses only on obtaining semantic segmentation errors in everyday and medical images, but most were limited to datasets with a known number of instances. There are also several attempts to extend Bayesian uncertainties to object detection and instance segmentation tasks. For example, Miller proposed to cluster the detection boxes from multiple forward paths and a single-shot detector to obtain spatial and classification uncertainties. There has also been an attempt to extend detection box clustering to mask RCNN for instance segmentation. However, there has been little discussion on how Bayesian uncertainties can be used to improve inference of downstream measurements to help with clinical decision-making. In our work, instead of visualizing segmentation uncertainties, we focused on the aspects on how to use these uncertainties to improve clinical measurements. Sample average predictions from Bayesian neural networks may produce confidence values that scales more linearly with the probabilities that the model makes a correct prediction. However, interpretation of the output from BNNs is important, as it would allow us to better understand to what extent the model can be improved. One way to quantify uncertainties is the predictive entropy. Alternatively, classification uncertainty can also be decomposed into allotoric and epistemic errors. Allotoric errors can be interpreted as uncertainties inherent to the ambiguity of the data, whereas epistemic errors measures the uncertainty due to limitation of the model. For segmentation tasks, these uncertainty measures are evaluated pixel-wise. Based on these uncertainty, we can derive a confidence score for each object instance K by taking 1 minus their mean over the segmentation mask. The confidence score in each instance would allow us to obtain a weighted histogram of the measurement of the dataset or of the slide as illustrated in the schematic below. In the following experiment, we will thoroughly test whether the confidence-weighted measurements, as proposed, perform any better than the unweighted measurements. So what kind of measurements are we interested in histopathology? Well, there are many measurements we can make, but the obvious ones are the area of the tissue, the aspect ratio by measuring the major and minor axes, and in our case we are looking at the proximal tubules in renal biopsies, and we are interested in measuring the distribution of stains, as in how close they are to the edge of the segmentation boundaries. So we invented these measurements that we call Y-gamma. where we evaluate the summed pixelwise product between the distance transform of the segmentation mask D and the pixel values X. There could be an endless list of other measurements, such as distance between different types of tissues within a slide and morphological descriptors, but here we'll only focus on these three measurements. The datasets we use are for a project to improve organ assessment of kidney transplantation. We'll be using these datasets for our experiments. First, we have our training set from kidneys used in a reperfusion experiment. These were originally stained with H&E stain. Then we have our test datasets. These were pre-implantation biopsies from kidneys that have been transplanted. They were stained and passed, which stains differently from H&E in the sense that it highlights connective tissues in pink. Because the staining protocol of the datasets differ, the training set was converted to pass using a cycle gun prior to the context of this paper. All networks in this paper were trained using the fake pass images. Finally, in order to experiment how our proposed scheme improves measurements on data that differs gradually from the training sets, we have also synthesized a dataset based on the reperfusion experiments. We would like the synthetic data to meet four criteria. Firstly, we would like the dataset to deviate progressively from the training data. Secondly, we want them to be visually diverse. Thirdly, we would like to control these visual changes using a single parameter. Finally, and most importantly, we need to know the ground truth segmentation mask of the synthetic data. So we have designed a pipeline to generate this dataset. We train a variational octoencoder to vary the morphology of the ground truth mask, and based on this mask we synthesize past-stained tissue patches. The mask consists of 5 classes: background, tissue boundaries in red, tubules in green. There are 2 additional rarer classes that are beyond the context of this experiment. The background class may contain tissues that have not been accounted for by our annotation scheme. We want to prevent the background from collapsing into a single texture, as well as to produce greater diversity in our synthetic images. To this end, we train a bicycle gun to translate the synthetic segmentation mask into past-stained images. We train a bicycle gun model using the default schematic from tool. The model is trained based on the reconstructed mask sigma equals 0 from the VAE, which are generally smoother than a hand-annotated mask. These are paired with the image patches from the reperfusion dataset. Here are some examples of our synthetic images. The top row are mask output from the VAE. The second row are images generated from the bicycle gun based on the mask on the top row, using the encoded latent vector and the bicycle gun. The third to the last row are also generated from the corresponding mask of the top row, but we resample the latent vector in the bicycle gun. Although we have generated 98,000 images, a significant portion of them do not resemble the mask, so we have selected 39K images for the subsequent experiment based on similarity between the reconstructed images, i.e. the second row, and the corresponding mask. So here's a schematic for our main experiment. We have a workflow to obtain tubule instances in our datasets and perform histological measurements over each instance. Then we obtain the distribution of the set measurement, and we want to see whether weighing the instances by the proposed confidence measure improves the distribution estimates. In order to demonstrate that our model is robust to the choice of hyperparameters, we perform our experiment based on different histological measures and different BNNs. We train 2 types of BNNs, a standard unit with MC dropout at test time, and a unit with base by backprop layers. Details of the network are described in section S2 of the supplementary material. One thing to note is that the hyperparameters of the experiment were originally tuned for the unit with MC dropout and had not been optimized for the base by backprop network, so we did not report a direct comparison of the 2 networks' performance. But intuitively speaking, despite the lack of tuning of the latter, we are already getting better IOUs in a base by backprop network. We compared distribution of histological measurements obtained from the predicted instance segmentation mask against those obtained from the ground truth mask using the Weissenstein distance. We define an evaluation metric delta WD by subtracting the estimated distribution from the baseline, that is, measurements derived from the unit without MC dropout. Here is one of the results figures from the paper. The plot shows delta WD for Y gamma. A more negative value means the measurement resembles the ground truth more closely. The x-axis shows how the results evaluate on different subsets of the test data. The far left of the x-axis shows delta WD on the real test datasets. The other labels on the x-axis shows delta WD evaluated on a synthetic dataset with different sigma VAE. The first red line here shows how the measurements from a sampled average MC dropout unit compares with the baseline. The second line here shows that if the results are weighted by confidence derived from epistemic errors, the distribution gets a little bit closer to the ground truth. Improvement is a bit greater when weighted by confidence derived from aleatoric errors. Then we get the greatest improvement when instances are weighted by the predictive entropy. While the red lines are results obtained from the encoded synthetic images, the green lines here show the corresponding improvements one would get on the resampled synthetic data. The former tends to have closer resemblance to the training data. The results from the other measurements and the two BNNs are in the paper. Summarizing all the figures, we generally see greater improvement when our method is applied to datasets with lesser resemblance to the training data. If we normalize the results by the WD obtained from the unweighted instances to CW0, we can compare the improvement of confidence weighting on the different measurements. The table on the bottom shows the normalized entropy-weighted WD averaged over the different sigma VAEs in the previous slide. We note several observations. Firstly, improvement is greatest for Y gamma and smallest for the major axis. We suspect the reason is because major axis measurements are generally more robust to segmentation errors, as it requires more misclassified pixels to change the size of an instance's bounding box. Secondly, improvement is greater on images with lower resemblance to the training data. Thirdly, improvement is greater for synthetic dataset than the real test dataset. The second and third observation suggests that our proposed approach may be particularly useful for improving estimations when evaluating cross-domain datasets. Consistent improvement can also be seen if we use the Jensen-Shannon distance instead of WD to compare distributions. However, WD is preferred as JSD tends to large values if PDFs are disjoint. Let me give you some intuition as to why this weighting might work. The figure shows distribution of instances as a function of the predicted histological measurement versus their mean entropy. It appears that the smaller instances, say those smaller than 1000 pixels, tend to have higher entropy. Segmentation uncertainty is usually higher around the boundaries, so this may give smaller instances a higher mass average entropy. Our algorithm may have also picked up more false positive small instances than larger ones, so weighting them with a smaller contribution makes sense. Some of you may wonder, why can't we just discard instances with the highest uncertainty? Well, if we do, we'll be introducing a hyperparameter, which is hard to find. In particular, we find that in our test dataset we have slides that suffer from artifacts not present in the training data, so setting a hard threshold would render many slides useless. The plots here show how the estimated distributions compare against the ground truth if we reject instances above a certain entropy. You notice that our proposed method, that's the red solid line, CW1, performs just as well as instances not weighted, dashed line, CW0, with around 30% of instances rejected. In practice, it may be very hard to find where to cut off the poorly segmented instances. So in conclusion, we propose a method to improve histological measurements by weighting tissue instances with confidence measures derived from BNNs. To demonstrate the robustness of our method, we generated a synthetic dataset that progressively differs from the original training data. Consistent improvement can be seen in measurements with confidence weighting, in particular with weighting derived from entropy. Generally, we see that the proposed method gives us greater improvement on data with less resemblance to the training data. This suggests that our approach may be particularly useful when applied to cross-domain datasets. Thank you very much for listening.